Welcome to video for Lecture 9, Section 3. In this video, we will describe a procedure to be used to linearize nonlinear equations or terms that we need to include in our differential equations that we need to transform into the Laplace domain. It turns out that Laplace transforms cannot handle nonlinear elements. In the previous video, we talked about liquid levels in tanks and flow from tanks. You may have noticed that we always assumed laminar flow, so that we could use the equation Q equals Z over R. Well, you may remember from your fluid class that not all fluid flow is laminar. So we need a way to handle nonlaminar flow, which has a nonlinear term. We will also illustrate a nonlinear term for the fluid heater problem, when both the temperature and the fluid flow rate vary with time. This material is covered in section 11 of the course packet. Many of engineering processes have nonlinear elements. The two examples that we will be using for this video is turbulent flow and when two variables that vary with time are multiplied together. If Laplace transform cannot handle nonlinear elements and we have engineering processes that involves nonlinear elements, we need a way to linearize the elements. The technique we will use is an approximation, so the final results are not as accurate as an analytical solution, but the Laplace transform process with linearization will still provide us with useful information. The method we will use is the Taylor series expansion. This is the same Taylor series expansion that we used in the uncertainty analysis we did earlier in this semester. As we did before, we will neglect the higher order terms. This graph shows a relationship we will use commonly in the course when we have turbulent flow from a tank. When we had laminar flow, we said Q equals Z over R. For turbulent flow, we will use Q equals C times the square root of Z, where Q is the flow rate in, say, liters per second, and Z is the liquid level depth in centimeters. C is the coefficient that includes the fluid flow resistance. From the graph, we can see that the flow rate is nonlinearly related to the fluid height. The first we do is to take the derivative of Q0 equals C times the square root of Z. We get dQ0 over dZ equals 1/2 times C times Zs to the power of minus 1/2. We will need the derivative for the Taylor series expansion. The next step is to find the Taylor series expansion of the equation or term with a nonlinear element. As we did with the uncertainty analysis, we will use only the first derivative terms in the Taylor series expansion. So for this case, the Taylor series expansion of the outlet flow will be Q0 equals Q0 of Zs plus dQ0 over dZ times Z minus Zs. We can now define deviation variables and write the differential equation for the fluid depth Z as a function of the inlet flow rate deviation variable. Given that Z at time t equals 0 is 0, we can take the Laplace transform of our differential equation with the deviation variables and write the expression as a transfer function. Z of S over inlet Q of S equals R of t over tau times S plus 1. As before, tau equal A times R of t, and from the linearization process, R of t equals 2 times Z at steady state to the 1/2 power over C. So using the Taylor series expansion allows us to take a turbulent flow expression with a nonlinear relationship between outlet flow and the fluid depth and convert it into a first-order problem that we have gotten before. One of the key things to remember is that if a fluid flow rate problem has turbulent flow, you need to use these equations. As I have said before, I will not be expecting you to develop these equations. When you get a problem with turbulent flow, you can go ahead and use these equations directly. There is another common type of problem for which we need to use the Taylor series expansion to linearize part of the equation so that we can use Laplace transform to solve the problem. The problem is when two time-dependent inputs are multiplied together. We have avoided that situation before by assuming only one input could vary. But in reality, several inputs could vary, and if we want to analyze the problem with two or more varying inputs and they are multiplied together in differential equations, we will end up with a nonlinear term. Here is the time-dependent differential equation we used previously for the fluid heating problem. If we multiply out the expression, we get a term where the fluid flow rate V dot is multiplied by the inlet fluid temperature Ti. This produces a nonlinear term if both the fluid flow rate and the inlet fluid temperature vary. We can simplify the problem and assume one is constant, but we can get better results using the Taylor series expansion to linearize the term. Here is the Taylor series expansion for the product of V dot times Ti. The first term is the product of the two steady-state terms. The second term is the partial derivative of the product V dot times T with respect to temperature, times the difference between the time-dependent temperature and the steady-state temperature. The third term is the partial derivative of the product V dot times T with respect to V dot, times the difference between the time-dependent flow rate and the steady-state flow rate. The partial derivatives are evaluated at the steady-state flow rate and the steady-state temperature. The partial with respect to the inlet fluid temperature is equal to the steady-state flow rate. The partial with respect to the flow rate is equal to the steady-state inlet temperature. After substituting in the terms and simplifying the expression, we get the equation at the bottom of this slide. We can take this expression and substitute it into the original time-dependent differential equation describing the fluid heating problem. The details are in the course packet. The next steps are to write the steady-state equation, take the difference between the differential equation and the steady-state equation. This produces terms that we can use as deviation variables. Then we reorganize the equation, divide through by the flow rate V dot, and define the time constant as the volume V over the flow rate V dot. After we do some more rearranging, we can take the Laplace transform. More details are in the course packet. Finally, we get the Laplace expression for the outlet fluid temperature deviation variable in terms of the electrical energy input deviation variable, capital Q, the inlet fluid temperature deviation variable, capital Ti, and fluid flow rate deviation variable, capital V dot. We are not able to write the expression as a transfer function in the form of output response over input function because we have two input functions for this expression, capital Ti and capital V dot. This shows the block diagram for the equation we found for the fluid heater problem with two variable inputs, the flow rate V dot and the inlet flow rate temperature Ti. Capital Q is the amount of electrical heat added to the fluid to change the outlet temperature T. This brings us to the end of this video about linearization. Please write down any questions you might have and bring them into class.